Hey y'all, we are Memphis University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today what we're going to be doing is we're going to be continuing our basic derivative unit topics. And this topic is actually going to be easy compared to some of the other videos in this playlist like absolute value or limits, continuity, and differentiability. So this one actually will be basic. And what we're going to try to answer is the question when to take derivatives. So we practice a lot on how to take derivatives. We've done the power rule, we've done the product rule, the quotient rule, and the oh so beautiful chain rule. And now what we want to know is when should we do this? So basically what we're going to talk about is certain words on an AP exam or on a college calculus exam is that right when we see those certain words, we are going to take a derivative. So first off, we're going to list these words out and then we'll practice with some examples. And also, we're not going to just practice with words, we might practice with notations as well, so that you get familiar with all the notations that denote a derivative. Finally, we're going to compare this to another concept that is pretty similar. It's going to be algebra slope instead of calculus slope, and that will be average rate. So let's get started. So the first thing I want to talk about is just when to take a derivative. So let's just list it out. When to take a derivative. So let's say you're given f of x and y, like f of x equals blah, 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 or y is equal to blah, 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 blah. Obviously, when you take a derivative is when you see that f prime of x or y prime of x. So f prime of x, you would take a derivative, of course. But you would also take a derivative when you have multiple tick marks, and that just means take multiple derivatives. So for example, if you have y double prime, that just means start off with y, take the derivative, that would be y prime, then take the derivative of that. So that's y double prime. Same thing with y triple prime. So y prime, y prime, y double prime, y triple prime, where as you go down, you take derivatives step by step by step. Of course, we don't want to have so many tick marks if we want to take like 17 derivatives. So if we take enough derivatives, eventually we write it in parentheses. So this would be, for example, taking 17 derivatives. You take one derivative, then you take another, then you take another, then you take another, until you hit the 17th one. So hopefully this notation is pretty clear. This is the notation that people are used to. But let's not forget our friend Leibniz. Let's go over his notation, which is actually better notation, but because it involves fractions, it sometimes scares students off. So if you're given a function y is equal to something, then you'll be taking a derivative when you see dy dx. So dy dx just means the derivative. So this is the same thing as y prime. So what about multiple derivatives? What is the second derivative? Just keep in mind that the second derivative is going to look like this. d2y over dx squared. This one will mean take the derivative, then take the derivative again. The 2 is in a weird spot, but that's because d dx by itself means take a derivative. So it's d dx squared. So you're taking the derivative and then you're taking the derivative. So that's why it's this form. And if you want to write multiple derivatives, for example, you can write d4y over dx to the fourth. This is just the fourth derivative, y quadruple prime. This is y prime, this is y double prime, y triple prime would be d3y over dx cubed. So you can see that the notation is a little bit more annoying to write, but it is a little bit clearer because you know what variable you're taking the derivative of with respect to. So that's how you write those derivatives. Keep in mind that as we take multiple derivatives, which we'll try to do in this video, one of the rules of thumb is that you should simplify each derivative as you go. Take one derivative, simplify it a little bit, and then take another derivative. Usually that makes the derivative easier to take in successive steps. So those are the main reasons why you take a derivative. It's very clear because this is a function. The question says take a derivative. But what about some English words? Well, remember derivative is instantaneous rate of change. So if you want to find the instantaneous rate of change, you're going to be taking a derivative, like find the instantaneous rate of change in f of x. Well, I'm just going to take a derivative, and usually it's add a number because it's instantaneous. So we're going to take the derivative, plug in a number. What's another way that we've seen before, perhaps in a previous video, why you take a derivative? Well, one of the main ways is equation of the tangent line. So if you want to find the equation of a tangent line, well then what you're going to do is you're going to take the derivative. So why are we taking the derivative? Well, a tangent line, for a line you need a point and a slope. the word tangent means that the slope is going to be the derivative. So in order to find the equation of the tangent line, while derivative might not be in the question, it is a derivative question actually, because right when I see tangent line, I think, oh, I need to take the derivative to find that slope. So once you see these words, you're going to be taking the derivative eventually. Then there's particle motion. So now we're going to introduce a little bit of physics, but there's three main functions we're going to talk about: position, velocity, and acceleration. So position. And when we say velocity, we mean an instantaneous velocity. The velocity at t is equal to 7 or something. So it's going to be position, velocity, and acceleration. When we see these words, we're also going to take a derivative. So for some reason, we use s for position. I don't know exactly why, but a lot of books use s for position, so that's what I'm going to do right here. For velocity, we use v, and for acceleration, we use a. But there's formulas where these functions are related by derivatives. So what's the rate of change of your position? Think about when you're driving along the road there. So what's the rate of your position? Well, that's going to be velocity. So s prime is equal to velocity. What about acceleration? Well, that's how fast your velocity is changing. So it's the instantaneous rate of change of your velocity. So v prime is equal to acceleration. But if s prime is equal to v, then that means s double prime is equal to v prime. So this is why we take derivatives. So for example, if the question is given a position, here's your position along the road. Now try to find the velocity. Well, I'll just take one derivative and plug in a time. If we're given its position and they say, now try to find acceleration, well, what I'm going to immediately do is take two derivatives, potentially simplifying those derivatives as I go, and then I'm going to plug in a point. Finally, if I'm given just velocity and I want to find acceleration, well, I'm just going to take one derivative. So just one derivative as you go step by step by step. We're not going to be able to go backwards until quite a bit later. That's antiderivative integrals. So for now, we're only going to go this way: position, velocity, and acceleration. So these are the main ways that we're going to see derivatives pop up. Right when we see this sort of notation, or if we want this to question, or we see these phrases, we know that we need to take a derivative, and we'll practice a few of these throughout this video. Keep in mind that there are more times that you do take derivatives. The main ones being for shapes of curves, which will be a later unit, where you want to see where a function is increasing or decreasing, where a function is concave up or concave down. That does involve derivatives, but for now, we're just going to keep it just like this. If you want, watch our shapes of curve unit. It's a very big unit where you determine the properties of graphs of functions without actually graphing the functions by drawing sign charts of f prime and f double prime. So be on the lookout for that. That is very key. But for now, we're just going to keep it at this level. So let's do a few examples. So I'm going to erase this. So you never should miss a derivative question because you just didn't memorize the derivative. So let's start off with y is equal to something like 2 over x squared plus 3 over x. And what I want to find is y double prime. So again, all you do is, you can't go straight from y to y double prime. So what we need to do is we need to take a derivative. So we're going to first end up at the first derivative, and then we'll end up at the second derivative. But even if we're taking multiple derivatives, we should use our derivative rules to our fullest advantage. And in this case, I don't want to do quotient rule because that would be quite nasty. Remember that if you have a number over x, what you should do is change that to a negative exponent so that you can do power rule instead. So it's 2x to the negative 2 plus 3x to the negative 1. X squared being in the denominator is the same thing as x to the negative 2. These are just fun little exponent rules that we learn in algebra 2 maybe. I'm not sure. So now let's go for the derivative. Notice it's so much easier using the power rule. Just take this power in our little hands and bring it to the front. Because there's a 2 there, it will be 2 times negative 2, which is negative 4x. And then we're going to subtract 1 from the old exponent, so it's going to be minus 3. Then we're going to take the derivative of 3x to the negative 1. Well, again, we're going to drop that negative 1 to the front, so that'll be minus 3. So we can change that to minus 3, x to the minus 2. Again, just taking the power, dropping it to the front, and subtracting 1. Now let's go for the second derivative. So I'm not going to rewrite this first derivative. Again, you simplify it as you take multiple derivatives. This is the most simplified form because it's ready for the power rule. So again, all we're going to do is take it to the front. That's going to be 12. because negative 4 times negative 3 is 12. X to the negative 4 now, subtracting 1 from the exponent, bringing the negative 2 across, so it's plus 6. Negative 2 times negative 3. Finally, it's x to the negative 3. And this is the second derivative. Again, nothing too bad, just taking one derivative after the other. One thing to keep in mind is that sometimes this might not be the form of the derivative or the second derivative on a test. So if you want to, you can change it back to a fraction. Oftentimes, that's a nice step. So basically, we change things, fractions to negative exponents to take the derivative more easily with the power rule. But once we're ready to work with it, for example, if you wanted to plug in a number actually, it's best to write it in this form. Like if we wanted to plug in 1, it'd be pretty easy. It'd be 12 plus 16, which is 18. But this is basically all review. So let's try to change it to be in terms of Leibniz's notation. So I'm going to erase all this. Just a nice, easy second derivative. Let's go for something a little bit harder. So let's choose a variable here that's not x and y so that we're used to things that are not x and y. A lot of my students only prefer x and y's, but we can use any variable we want. And sometimes teachers are crazy sort of gals and guys. So what we're going to use is we are going to use different variables. So in this case, I'm going to write n. So this is going to be my y because it's usually denoted with a capital letter. And then my function is going to be e to the, let's say, 3s. And what I want to do is I want to take the derivative. I want to find this guy right here. Let me just write it out first, and then I'll try to explain what we're trying to do. So this is going to be my guy here. And then what we want to do is we want to have this vertical bar here, and we're going to write this. Let's say 2. So what does this mean? What does this weird hunk of math mean? Well, again, what this means is that what we're going to do is we're going to take our function. First off, keep in mind that the x coordinate is usually on the bottom, or the first coordinate, the independent variable. So usually it's x, but now it's going to be s. Then my top variable, my dependent variable, is written on the numerator here. So that's usually y, but now it's going to be capital M. What does this 4 mean in these two spots? Well, it just means I want to take the fourth derivative. So I'm going to take this function, take one derivative, that's the first, then another one, the second, then another one, the third, and finally get to that fourth derivative. What does this vertical bar notation mean? Well, what it says is find the fourth derivative as I just described, and at the very end plug in 2, and you'll end up with a number. So let's do this question. So again, we're going to start off with this and go for this guy right here. So the first derivative, which we write as dm over ds. First, let's take one derivative. Keep in mind that, again, you need to be careful with your rules, product rule, chain rule, quotient rule. So what's the derivative of e to the 3s? Well, the derivative of e to the x is e to the x. So it's going to be e to the 3s. But we do need to multiply by 3 because that's the derivative of the inside function. That's the chain rule, of course. So just be careful that there should be this times 3. If you want, you can put the 3 in the front because usually people like the 3 in the front. So I'm going to do that. So now I'm going to take the second derivative because, again, I have to take all the way up to the fourth derivative. So let's just keep going. Second derivative time. So I'm going to take the derivative of this one right here. Notice there's a 3 in the front, and anytime you have a constant times a function, you just write that constant down and then you multiply by the derivative of the function. So we're going to have a 3. Now we need to multiply by the derivative of e to the 3s, but we just did that. It's going to be e to the 3s, but times 3. So there's actually a lot of 3's here, so let's talk about it. This first 3 came from the first derivative. There was just a 3 in the front. The derivative of a constant times f of x is a constant times f prime of x. And then this was the actual derivative of e to the 3s. Why is this times 3 here? Well, again, that's the chain rule. As I take the derivative of e to the 3s, there's a little inside function that I have to be wary of. The derivative of that 3s is times 3. So that's the second derivative. We could go for a third derivative automatically, but I'm not going to do that because remember my nice rule of thumb. It's easier if you simplify the derivative as you go. I know this is a very exciting process and you just want to keep taking derivative after derivative after derivative, but it's nice to just pause a little bit and be like, you know what, I'm going to multiply this 3 and 3 to become 9 so that when I take the derivative in the next step, it'll be slightly easier. So let's do that. So what's the derivative of 9 e to the 3s? Well, there's a 9 in the front, so we're just going to write 9 here. And then finally, what's the derivative of e to the 3s? Well, again, it's e to the 3s times 3. So hopefully you see that as we take derivatives, the derivatives aren't changing very much, but every single time we multiply by 3. So there was a times 3, then there was a times 9, and finally for this one there's a 27. Another times 3, e to the 3s. So what's the fourth derivative? Again, I simplified the third derivative to make the fourth derivative a little bit nicer. But what is this fourth derivative? Well, it's going to be the derivative of this, 27 e to the 3s, and then one final time we're going to multiply by 3. Again, every single time you're going to multiply by 3 because you're still taking the derivative of e to the 3s, and 3s has an inside function of 3, and that's what the chain rule tells me to do. And I never not listen to the chain rule. Finally, what's 27 times 3? That's 81. So we have 81 e to the 3s. So how do we finish this question? Well, again, this vertical bar notation tells me that the answer isn't going to have variables because you're going to plug in s for 2. So at the very end here, all I want to find is the fourth derivative. Let's use a capital M over ds to the fourth. So what we're going to do is we're going to find the fourth derivative. So to find the fourth derivative, we're going to plug in the number s is equal to 2. So it's going to be 81 times e to the 3 times 2 because I just replaced this s with 2. So it looks like my answer is 81 e to the 6. And we're good to go. So again, not the hardest question in the world. Just take multiple derivatives, be very careful with the chain rule, and then plug in your number at the very end. Chain rule, chain rule, chain rule, chain rule, chain rule, especially for these small little ones. So let me erase this and let's practice with more examples. So let's do a tangent line question because we're pretty used to that question. So we can do that question hopefully pretty fast. Let's say we have a function. We're going to write x squared plus 1 over x. And what we want to do is we want to find the equation of this, the tangent line. Find the equation of the tangent line. 2f of x, let's say at the point x is equal to 2. So again, the main point of this video is when to take derivatives, and the answer is you take it a lot, and one of the words that prompts you to take the derivative is going to be equation of the tangent line, equation of the tan line, because again, tangent lines are point and slope, where slope is the derivative. So let's try to find the point first. So remember, to find the point, all you do is you take your x coordinate 2, and then you plug it into the function to find your y coordinate. The point doesn't require any calculus. Calculus deals with the derivative, meaning the slope. So in this case, when you plug in 2, looks like we're going to get 5 halves. So that's not too crazy. Now let's go for the slope. Again, the slope is the derivative when you have a tangent line. And when you're taking these derivatives, just be careful with the rules. Don't try to confuse this with L'Hopital's rule. The derivative isn't just 2x over 1. You have to do quotient rule. So it's going to be low d high minus high d low over low low. So it's going to be low d high, which is just 2x, minus high, which is going to be x squared plus 1. Keep in mind that I'm writing this high all in parentheses just to be a little bit safe. D low just times 1, and then finally divide by low low. So low d high minus high d low over low low. You could simplify this if you want to, but because we know the point, we know the x coordinate, let's just plug in the x coordinate right now so that we don't have to deal with variables. We only have to deal with numbers. So in this case, we're going to plug in 2. It's going to be 2 times 2 times 2. I'll do that later. Then it's going to be 2 squared plus 1 times 1. Of course, we don't have to write times 1. And then finally 2 squared. Just be careful with math as you're simplifying. Don't butcher your work. Don't make a mess of such beautiful sort of work that you've already created. For example, don't pass out these 2 squareds. Remember that in order for fractions to cancel out, the term has to be in every single one of these. 2 squared is not being multiplied here, so you can't cancel that out. So we just had to do some old school math here. 2 times 2 times 2 is 8. 8 minus, well, this is 4 plus 1. 2 squared plus 1. So that's 5, finally over 4, so this is going to be 3/4. So again, why did we take the derivative? Because we saw the words equation of the tangent line, and tangent line requires me to take the derivative to find slope. So this is going to be my slope. I'm going to find the equation. The equation is going to be y minus 5 halves equals the slope, which is 3/4, times x minus the x coordinate, which is 2. So this is going to be my answer. Y minus the y coordinate equals slope times x minus the x coordinate. And that's how you do equation of the tangent line questions. We've seen that all before. So for the last half of the video, I want to compare instantaneous rate of change versus average rate of change. So let's do that carefully, and then we'll do 2 examples. So I'm going to erase this real quick. I'm going to erase this, and then let's write some examples. Not my prettiest work here. So I'm going to write, what's the difference between instantaneous rate of change? Instantaneous, let's see if I can spell it right. I usually can't. I think that's right. Versus average rate of change. So first off, instantaneous rate of change is at a point. Find the instantaneous rate of change of this function at x is equal to 3 or t is equal to 1. So this is going to be at a certain point, at a given point, or time, or x. An average rate is find the average rate over an interval. You don't find it at a time because you need to be able to take the average of something. So it's going to be over a time period, like from 2 to 6. So this is going to be over a time period. Keep in mind that over a time period, that means from, sometimes the time period is a little bit weird. For example, sometimes they just use English words and it's hard to convert from English words to math words, but we'll talk about this later. But sometimes they say like first 5 seconds. First 5 seconds would be from 0 to 5. That would be your time period A to B. Sometimes they start from like noon to 4 and they signify, well, noon is going to be time 0. So you would want to go from 0 to 4 and not like change to military time, for example. But again, the main thing is instantaneous rate is at a given point. Average rate is going to be over a time period, which means that instantaneous rate, as we talked about before, that's going to be the calculus slope. The calculus slope meaning the derivative. What is average rate of change going to be? Well, because it's over a time period, you have 2 points. It's going to be our old friend algebra slope. So algebra slope. So it's just going to be y2 minus y1 over x2 minus x1. People love the average rate question because when you see average rate, it's one of the only questions on the AP exam that you don't take derivatives or later on integrals. You just do algebra slope instead. So usually they're pretty minute. Keep in mind that we will learn another formula for average rate that will involve integrals, but we're not ready for that yet. So for now, think about average rate as algebra slope. So instantaneous rate is calculus slope, average rate is algebra slope. So let's talk about it in the context of particle motion, which is our main sort of real life utility of calculus, if you like utility, which I don't like too much, but we're going to talk about it. So first off, we're going to talk about instantaneous velocity. Well, instantaneous velocity is just going to be the calculus slope of position. Remember, we're going to denote it with s's. So this is going to be the calculus slope of position, s prime of t. Average velocity, which can be rewritten as the average rate of change of position, just like instantaneous velocity could be expressed as the instantaneous rate of position. Average velocity is going to be your algebra slope, and it's going to be the algebra slope of the function. Like how this was calculus slope of the function, average velocity is going to be algebra slope. So it's going to be s of b minus s of a over b minus a. Similarly, let's just try to do it with acceleration. So instantaneous acceleration, if I can get those words in, that's going to be v prime of t, the derivative of velocity, the instantaneous rate of change of your velocity. How much you're accelerating is how fast you're going changing. So for example, you're going 30 miles per hour, 40 miles per hour. I don't know how fast you drive, but if you step on the accelerator, that's why it's acceleration, you'll change your velocity, how fast you're going. You'll be going 60 miles an hour, 70 miles an hour, 80 miles per hour, however fast you like to drive. So average acceleration is really similar to average velocity. Again, it's an average rate. It's going to be algebra slope of the velocity formula. So it's going to be v of b minus v of a over b minus a. So again, hopefully you see the difference between these two rates. They're both rates, and calculus is the study of rates, but you want to know which rate you're dealing with. When you're dealing with instantaneous rate, that will be at a given point, it will be calculus slope. So for example, SVA, where you're taking derivatives as you go. Average rate of change is a little bit easier. It's over a time period, so that's why you have y2, y1, x2, x1. So you're able to form average slope, algebra slope, and then average velocity is an algebra slope, average acceleration is an algebra slope of the correct function. So let's practice this real quick. So I'm going to erase this. I'm going to erase this guy. Going to erase this guy. So let's start off with a particle motion question. So let's say our position is given as t cubed plus 3t squared minus 2t plus 1. So I just made up some random numbers. And what we're going to do is, for the first question, we're going to try to find the acceleration at t is equal to, let's say, 2. And then the next question what we're going to do is find the average acceleration. So it's a completely different question when you add the word average, but it's average acceleration. And remember, average is over a time period, so I'm going to say over the first 2 seconds. So again, the first one is at the specific time 2. This one is over the first 2 seconds. So this one doesn't use the word instantaneous, but hopefully you know that it is instantaneous because it's at the number 2. So this is going to be instantaneous rate of change. It doesn't have the word average. So this is our calculus slope. So what we're going to do is we need to first find acceleration. But remember that s prime of t, the derivative of position, is velocity itself. Unfortunately, you can't skip straight from position to acceleration. That would make life a little bit easier, but we can't skip steps. We have to go midway to hit that velocity and then take another derivative to go for the acceleration. So what's the velocity here? Well, it's just the power rule. Taking the power to the front, subtracting 1. So it's going to be 3t squared for the first one. Then you bring the 2 down. There's already a 3. Let the 2 and the 3 mingle. That's going to get plus 6t. Because you do 2 minus 1. What's the derivative of minus 2t? Well, what's the derivative of any constant times x? Well, it's that constant. Same thing with this time example, keeping in mind that t is the independent variable, so it's treated like our x. Probably should have mentioned that before. But the derivative of minus 2t is just minus 2. Finally, what's the derivative of plus 1? That's, of course, 0. Because any derivative of a constant is 0. So that's your velocity, but you do need to find acceleration, so you have to go one step further. So s double prime, remember, my marker might be dying here, but we're going to persevere and go on, which is the first derivative of velocity. The second derivative of position is the first derivative of velocity. Let me try to erase this and make it a little bit neater. S double prime. This is the a we want. So let's take another derivative. We're just going to take the derivative of the first derivative. That's the second derivative. Try to say the word derivative 10 times fast. It's kind of difficult. So we're going to let the 2 drop to the front again. So it's going to be 6t. Then we are going to take the derivative of 6t. That's just going to be 6. That's going to be plus 6. And then finally, we do want to find the acceleration at a certain time. If the question would just write the acceleration, our answer would be 6t plus 6. But in this case, they do want us to plug in 2, so I will plug in 2. It's going to be 6 times 2 plus 6. This is 18. So this is the answer. If you had units, if you don't know, every time you take a derivative, you divide by a time period. So usually position would be in meters. Then it'd be meters per second, for example, for velocity. And then for acceleration, it'd be meters over second squared. But let's see the difference between acceleration versus average acceleration. So for average acceleration, remember it's not calculus slope because it's the average rate of change of velocity. So what we want to do, instead of doing calculus slope here, we're just going to do algebra slope of v. So it's going to be v of what 2 points? Well, remember first 2 seconds means that we want to go from 0 to t is equal to 2. That's the first 2 seconds. And these are going to be our denominator of our y2 minus y1 over x2 minus x1, because the y's are going to be velocities, because that's the acceleration is the rate of change of velocity, and then our x's are going to be t's. So in this case, it's just going to be v of 2 minus v of 0 over 2 minus 0. So let's find this. We already found velocity in the previous step, but if this were the first question, I would have to take a derivative just to find velocity, and then I could do my average acceleration question. But for now, because we already took the derivative, let's help ourselves and sort of get help from us from the past. So what we're going to do is we're just going to plug in 2, It shouldn't be too bad. 2 times 2 is 4. 4 times 3 is 12. Then when we multiply by 2 again, it's going to be plus another 12, I believe. Finally, it's going to be minus 2. So this is V2. I still need to subtract V0, so it's going to be minus. V0 is going to be 0 plus 0. I don't have enough space, so I'm going to not write 0 plus 0. Let's see here. So instead, I'm going to just write minus 2. And then finally, it's going to be over 2. Again, average acceleration, average rate of change is one of the easier questions on the AP exam because it is just algebra slope. And we've done algebra slope so many times in our life, it's easier than the calculus slope. So it's going to be 24. Let's just do all this math. It's going to be 24 minus 2, that's 22, plus minus a 2, so that's going to add back to 2. So it looks like this answer is going to be 24 divided by 2, which is going to be 12. And again, if this were meters and the time would be in seconds, well, velocity would be in meters per second. And then if you do an algebra slope or a calculus slope, this unit would be meters over second squared. So we can add those units maybe. This was in meters, this was in times seconds. So this would be meters over second squared again. So notice that there's a huge difference between instantaneous acceleration versus average acceleration, which is really the point of this video, when to take a derivative or when not to take a derivative. Another way to phrase this is when do I do calculus slope or when do I do average, meaning algebra slope? Well, instantaneous is calculus slope. Just start taking derivatives, plug in a number. It's at a single number, the slope of the tangent line, where the tangent line is only touching the function at one point. Then we have average acceleration, average rate of change. Well, that's over a time period, so we have 2 points, and we just want to find the slope between those 2 points. So it's just algebra slope. So calculus slope is for instantaneous rate of change. Algebra slope is for average rate of change. Let's do one more example with a real world example so that we can say that any of this was meaningful. I'm not sure if after you watch this video if you agree, but let's just do one more example using temperature. So let's say we have this function right here. We're going to keep it generally pretty simple. Let's say we have a function called T. This is temperature, so we can write temperature. We'll write temperature on the bottom here. I will say it's in Celsius because I think it would make more sense if these degrees are in Celsius. Let's say it's going to be, let's keep it simple, T cubed minus 3t squared plus 2t minus 1. And what we want to do is we want to find 2 different questions. We want to find the average rate of change. So I'm just going to abbreviate this AVG, rate of change. I don't know why I abbreviated that and not abbreviated any of these words, but whatever. Of the temperature from T is equal to, let's say, 1 to T is equal to 3. And then what we're going to do is we are going to find the instantaneous rate of change, or just the rate of change. So sometimes they don't use the word instantaneous, they omit it. But again, it should be pretty easy to tell. Average rate of change will have 2 time periods. Instantaneous rate of change will only have 1 time period. 1 time because it's instantaneous at that one point. So find the rate of change of the temperature at T is equal to 3. So again, the goal is to try to decide which one is algebra slope, which one is calculus slope. Why don't you pause the video and just think about that one question. If you're feeling bold and frisky, you can actually do the question. You can do one with calculus slope, one with algebra slope, but at least try to determine which one it is. I won't look at you so that you don't have any pressure as you do this. It shouldn't be the hardest thing in the world. Let me unpause your video real quick. So let's talk about it. Let's see what we got. So average rate of change, because we have these 2 times, that denotes, of course, algebra slope. So this is going to be my first T, this is going to be my second T. So I can divide this by 3 minus 1. And what I need to find is just T of 3 minus T of 1. No calculus slope, no calculus at all. So what I'm going to do is I'm going to have to plug in 3 here. But plugging in 3 is actually pretty good by coincidence because you get 3 cubed minus 3 times 3 squared, which is also 3 cubed. So it's going to be 3 cubed minus 3 cubed. That's 27, but they immediately cancel out. So I think you're left with 3 times 2 minus 1, which is just 5. Then I have 3 minus 1. That's going to be 2 on the bottom. Let's find 1. When you plug in 1, it'll be 1 minus 3 plus 2 minus 1. These 1's cancel. So it's going to be minus negative 1. Of course, if it's minus minus, you just want to be careful with that. looks like this answer is just going to be 3. Let's try to put units here. Let's say that our time units were in days. So then what's the rate of change of temperature maybe in a certain city, like Memphis? What is the rate of change of the temperature in Memphis in Celsius? I don't know why we're using Celsius because I'm a Memphian and I have no idea how Celsius works, but the rate of change would be 3 degrees Celsius. So every single day, on average, the rate of change is increasing by 3 degrees. If it was negative, negative is okay when you have rates. That just means the rate is decreasing. So for example, in Memphis, the rate is increasing between t equals 1 to 3, on average 3 degrees. If it was negative 3, it would just be decreasing by 3 degrees. Finally, let's do this last question. Find the rate of change temperature at t equals 3. So meaning exactly as on the third day as it starts, what's the rate of change of the temperature? And that's the miracle of calculus. You don't need 2 points. You can find that exact rate of change. That's going to be the derivative. So it's going to be t prime of t. You do need to take the derivative. So it's going to be 3t squared minus, using the power, of course, taking the 2 down, bringing it to the front. That's minus 6t plus 2. The derivative of 2t is 2. The derivative of minus 1 is 0. So all we need to do is plug in 3 to find the right answer. When you plug in 3, looks like it's going to be a little bit difficult, so let me just do it on the side here. 3 times 9 minus 6 times 3 plus 2. That's going to be 27 minus 18 plus 2. So that means that this is going to be 9 plus 2, which I believe is 11. So it's going to be 11. And then let's put some units. So again, anytime you have a derivative, you just divide by the time period. So this one was in degrees Celsius per day. And this one is going to be in degrees Celsius per day. It doesn't matter if you're doing calculus slope or algebra slope, any rate will have the same unit. But hopefully you see the difference between these questions. Again, they're quite different because one of them is algebra slope and one of them is calculus slope. Try to recognize which one is which. Throughout this video, we talked about different ways to identify that it is a derivative question. The easiest ones were just y and then try to find y prime or y double prime. But even in Leibniz notation, like finding the fourth derivative, dm d4 to the m over dp to the fourth or something like that, that's when you take multiple derivatives. You might need to plug in a number. Of course, when you see equation of the tangent line, you also take a derivative, and same thing for these instantaneous rate of change. We did introduce a pretty big concept that we're going to keep coming back to over and over and over again throughout calculus, especially in the AB portion of the calculus exam, but also in the BC portion, also in college calculus exams, and that's particle motion. The 3 big functions are position, velocity, and acceleration. To go from one to the other, you just take derivatives. Position, take a derivative, you'll get velocity. Take another one, you'll get acceleration. And then finally, we did talk about, in depth, the difference between average rate of change and instantaneous rate of change. Average rate of change is just algebra slope. Instantaneous rate is just calculus slope. So average rate of change is just y2 minus y1 over x2 minus x1. It's nice to find the exact x2 and x1 and things like that. And then instantaneous rate, calculus slope, that's of course the derivative. But if you want more practice with this, if you want to try to see again keywords where you need to take the derivative like instantaneous rate of change, or if you want to do questions sort of to practice, do I want to do algebra slope, do I want to do calculus slope, be sure to check out our Girls Teach Calculus video that I'll link in the description below. It should be pretty useful as it provides you with these examples, including ones with particle motion. But until then, thanks again for watching. This has been our basic derivative topics unit. If you continue watching these basic derivative topics, hopefully you'll be pretty good for these derivative topics. If you're ready to move on, our next unit will be on shapes of curves, so be on the lookout for that. That's a big one, folks. That's our f increasing, decreasing, concave up or down, and we'll be taking derivatives in there, as alluded to before. But until then, thanks again for watching. Like and subscribe if this video was useful for you at all, and I hope to see you next time.